Okay. So, let us start that new topic which is called short time Fourier transform, STFT, short time Fourier transform. So, in this whole week we discuss about the STFT. So, STFT we have the two dimension, one is analysis, another is synthesis view we will discuss, and then do you discuss about that FT filtering view and that Fourier transform view, and then synthesis by filter bank summation and OLA methods, overlap add methods. So, all those things will be discussed during this week. So, what is STFT? Why STFT come into the pictures? Now, if I show you, suppose this is my speech signal, this is my whole speech signal is this one. Okay. Now, if I take the Fourier transform of whole speech signal, then I get a spectrum or frequency domain representation which consists of all average of all the variation. That means, if you see along the time, this axis is the time axis. So, along the time speech signal is not stationary. If you see the speech signal is changing, some voice, some different kind of voicing, then noise, then voicing, then silence, there is a different kind of voicing, then noise, again voicing. So, speech signal is changing along the time. Okay. So, if I have a long speech signal or I have a speech signal of a word or speech signal of a sentence, then I say if I take whole sentence at a time or whole word at a time, it may consist of several variation of the signal. That means, signal is not stationary along the time. So, if I take the whole signal and do the frequency analysis, I do not get that any conclusion, any information of different speech event what is happening. So, what I want? We want during the pronunciation different time speech signal property is different. I want to analyze that property which how it is varies across the time. So, if I want to do it, then what I have to do? I have to select a short segment of the signal and do the analysis. Next again I have to select the next segment and do the analysis. So, what I am doing, instead of taking the whole signal, I am taking a small portion of the signal. This is 1269 sample I have taken, then I take the frequency analysis. Okay. So, as you know in the recap that what is frequency analysis we are doing, that if you know that if x n is my time domain signal, then if I take the discrete Fourier transform or if I take the Fourier transform, then signal domain it is discrete, but frequency domain it will be continuous. So, if I take the Fourier transform, then what I get? I get x of n into omega, or if it is single frame signal, let us x omega. Okay. If it is discrete Fourier transform, then I get x of k, that I have already discussed in the Fourier transform view. If x n is my signal and if I take the Fourier transform, then in frequency domain it is continuous, but time domain it is discrete, and that is called DTFT, discrete time Fourier transform, discrete time Fourier transform. Once I both domain it is discrete, then I say it is DFT, discrete Fourier transform. So, FFT is nothing but an algorithm of implementation of DFT. So, once I get that omega is discrete, then I say it is DFT. That means, here omega is nothing but a 2 pi by n into k, where n is the length of the DFT analysis. That is recap of your review of DSP, the digital signal processing. Okay. Now, again you know that if I get that xk has a complex number, xa is a complex number. So, it has a two property, one is mod of xk, that is called amplitude and angle of xk, tan inverse imaginary by. So, this is phase and angle. So, if I take the spectra of magnitude only, then it is called magnitude spectra. If I take the phase only, then it is called phase spectra. So, if I take the time, this axis is the magnitude, this axis is the frequency and y axis is the magnitude of discrete Fourier transform, then I call this is a magnitude spectra. Okay. If I take the phase, so xk is nothing but in the form of a plus jb. So, what is the magnitude spectra? Root over of a square plus b square. If it is phase spectra, theta is equal to tan inverse b by a. So, if I plot the theta against the frequency, if this is the frequency axis and this axis is the theta, then I call this is a phase spectra. So, frequency analysis, we find out two kinds of spectra. One is called phase spectra, another one is called magnitude spectra. If you see, if I analyze it, frequency analysis, if you see this window, this axis is the frequency. If it is linear view, that means frequency scale is linear. If it is not linear view, then I say the frequency scale is log scale and this axis is the amplitude of the particular component. Okay. So, this spectra is nothing but a magnitude spectra. Okay. Now, if you see magnitude spectra of this portion of the signal, if I select this portion of the signal, it is different spectra. So, I can say the speech is not a stationary signal. So, I have to analyze the speech signal with a segment wise. So, instead of taking the whole signal, I have to take the signal part of a signal. Okay. So, I have recorded my voice of a sentence and it has 1 second, it has sampled at 16 kilohertz with 16 bit. So, each sample is encoded with 16 bit and sampling frequency is 16 kilohertz. Suppose I record a sentence which is 3 seconds long. So, if a sentence is 3 seconds long, how many sample will be there? 3 into 16k sample. So, 48k sample will be there. So, 48,000 sample will be there. If I take whole signal at a time, do the frequency analysis. So, during the sentence speech is not same. Sometime I said some consonant, sometimes some vowel, sometimes some consonant, sometimes consonant to vowel transition. So, all kinds of variation is exist. If I take the whole signal and draw the magnitude spectra, which is like this, if I take the whole signal and draw the magnitude spectra, that means whole signal and I draw the magnitude spectra, that is nothing but a average spectra of whole signal. I cannot get the local variation. So, what I want, instead of taking the 48000 sample at a time, I let us say I divide the signal with a some segment. Those are the segment. So, I divide the signal with a segment which is called 100 frame per second. That means, in 1 second I will analyze 100 frame. Okay. So, let us 100 frame. So, I have a segment, I want to analyze a segment which is nothing but if it is 16 kilohertz, it is 10 millisecond of each segment. Okay. So, 10 millisecond. So, you already know the framing. So, what I do? I cut a segment of the speech and do the frequency analysis. So, once I cut a segment of the speech, one segment, then it is called time is short time. And if I do the Fourier analysis, Fourier transform. So, this is called short time Fourier transform. So, I can say I frame by frame I take and analyze and I have to get back the same frame again if I take the inverse DFT. So, whatever modification I do in the spectral magnitude, then again I take the inverse transform to get the same frame back. So, that is called synthesis. So, analysis when I doing the transform. Synthesis, when I get back the signal again, is called synthesis. So, after analysis, after finding out that I get the magnitude spectra is like this, I modified the magnitude spectra. I can modify it. Once I modified it and again I take the inverse transform, I should get the signal back which is modified property. Okay? So, then once I get the signal back, that is called synthesis, the analysis part is called analysis. So, this is called, that is why this is the short segment of time is analyzed, that is why it is called STFT, short time Fourier transform. Okay? STFT. What is STFT? Now we know. Now, next topic is that, okay, so short time will be like, so what I am doing, so this is a time scale, if you see, this is my frequency scale. So, what is the maximum frequency of if I normalize discrete way? So, twice f, this is omega scale and this is f pi, twice pi is the f pi is the maximum baseband signal, and I analyze, let us for this time instant. So, this time instant I analyze. So, this portion of the signal I have analyzed, I get the spectra, then again I analyze for this time instant, I analyze, again I analyze for this time instant, this frame I analyze and get the spectra. Okay. So, if you see this one is that. So, now if I want to mathematically represent this thing, so what is this? This is nothing but a xm digital signal. Let us, it is infinite to infinite digital signal, let us it infinite to infinite or 0 to 4800 in case of real signal. So, if it is infinite to infinite, then I can say xm x n omega, x n omega. I want to find out the frequency response of this portion. So, this portion is 1, 2, 3. So, this is n, I can say this is n equal to 1, n equal to 2, n equal to 3, this n will vary. For this omega is nothing but a x of m, m equal to minus infinity to plus infinity. I have cut the signal, that means I have multiplied this signal with a window function which is n minus m. Okay. I just illustrate this one. What is this? Okay. Let us, this is my whole signal, this is whole signal x n. Okay. So, this is the nth instant n. I want to cut a portion of the signal. What I do from the nth instant, let us I want to cut L number of sample. So, what I will do from nth instant, I take the L number of sample this side. So, this is L length sample. So, once I cut it, means I am multiplying a rectangular window of L length. So, suppose this is my rectangular window. So, what I am doing, I inversing the time of the window this side and cut the signal. So, that is why it is n minus m, because m is varies in this axis. Okay. So, n minus m number of signal I cut and multiply it. Okay. So, what is this? This is nothing but a frequency domain, it is continuous. So, I can say this transform. So, it is frequency transform means this e to the power minus j omega m. So, this time domain it is discrete, frequency domain it is continuous. So, I can say it is nothing but a DTFT, discrete Fourier transform of x m multiplied by w n minus m, which is window function, this product, discrete time Fourier transform of this one. Now, if I want to make this omega is discrete, then it is called discrete Fourier transform. So, if I see that I am again this slide I have already explained. Okay. Okay, let us explain this slide also. So, if you see there is a time origin which is m, either will be with the window or we will the signal. So, if it is this one, then I call time origin is with the signal, because m is varies infinite m series, m is varies and x m is varies infinite. So, time origin with the signal itself, that is why window is clap back and cut the signal. Now, if the time origin tied with the window, then the same things I can write x n omega is equal to. So, time origin with the window. So, what I am doing? I am shifting the signal or shifting the window with the time. Okay. So, e to the power minus j omega n m equal to minus infinity to infinity x of n plus m omega n, sorry, omega minus m e to the power minus j omega m. Okay. In that case, I can say it is nothing but a e to the power minus j omega n dt f t of x of n plus m into omega minus m. Time origin tied with the window. So, I said the time is shifting with the window function only. So, one is that I have a signal, I can cut the signal. Another is that I have a signal, I have take the signal, I have a long window, I cut the window at a m number of time and multiply with the signal, rest at 0. Okay. So, in practical, what we are doing, in practical scenario what will happen? Time origin tied with signal, okay, let us forget about that part. So, suppose the example whatever I have given, so I have 3-second recording, so I have a 48000 sample. Okay. Let us I take 10 millisecond window. So, that means 160 sample. So, in 160 sample I take and I do the DFT, then again take the another 160 sample, then I do the DFT. Actually, what we have done, since there is a cutting effect, if I have a signal of long signal 4800 sample, I take a window size of let us 20 millisecond and then shifted the window 10 millisecond, that means 100 frame per second. So, that first I take 320 sample from 0th sample to 0 to 320 sample. Next analysis window, I will shifted the window only 10 millisecond. So, next I said 162 again 320. So, 320 plus 160. Again I said 322, 320 plus 320 to 320. So, that way I have taken that window, shifted the window with 50% overlap. Okay. Again I will come that later on briefly. So, STFT analysis with DFT view, discrete Fourier transform view. So, what I said, x of n omega, omega is continuous, is nothing but a m equal to minus infinity to infinity x of m w n minus m e to the power minus j omega m. Okay. Now, this is DTFT, discrete time Fourier transform. So, omega is continuous. Now, I want to make omega is discrete. So, how the omega becomes discrete? Omega is continuous in the frequency plane. So, what I do? I have a frequency scale, I have a DFT, DFT, discrete Fourier transform. Then the length of the discrete Fourier transform is involved. So, DFT length, if you remember the review of the DSP, there is a n is called DFT length. Okay. So, if I take the n number of DFT, n is the DFT length, that means 0 to 2 pi, whichever the discrete frequency, that 2 pi frequency scale I have divided in n number of samples. So, there is, so each division is nothing but a 2 pi by n. 2 pi is the highest frequency, which is Fs. So, if it is a 16 kilohertz signal and length of the DFT is 1000, then I can say each of the segment is 16 hertz. So, it is 0 to 16 hertz, 16 to 32 hertz. So, each of the segment is 16 hertz, which is twice pi by n, nothing but a Fs by n. So, I can say I can divide this omega with respect to k in term of discrete frequency, which is called k. So, instead of omega I can write x of n k, where I can write m equal to minus infinity to infinity, x of m will be same, w n minus m will be same. So, instead of continuous omega, I have divided the omega in term of 2 pi by k e to the power minus j 2 pi by k, 2 pi by n into k into m. Okay. That means, this omega has divided into 2 pi by n. Okay. So, x of n0, first component is nothing but a DC. Second component k equal to 1. So, it is 1. So, instead of k I put 1, first frequency, second discrete frequency, third discrete frequency. So, k has a relationship with analog frequency f. F is nothing but a 2 pi by n is the resolution into k. Okay. So, this is discrete frequency, discrete. So, once I do that, then this process is called DFT, discrete Fourier transform. So, I can write this representation is called DFT, this representation called DTFT, discrete time Fourier transform and discrete Fourier transform. Now, what is 2 pi by n? If you see 2 pi by n, okay, 2 pi by n is my frequency resolution. So, if I have a 16 kilohertz signal, 16 kilohertz is the sampling frequency and n equal to 1 kilohertz, 1 k, then I said every band is nothing but a 16 hertz. So, this is 16 hertz, this is 16 to 32 hertz, this is 32 to 48 hertz. So, I can say that Fs, the frequency scale is divided in a band. So, number of band is divided by number of band is represented by n. So, if it is n equal to 1000, that means number of band is 1000. If it is n equal to 64, then I can say 0 to Fs signal is divided in 64 band. 64 band. So, sometime this is called band number also, n is called band number also. I can say this is a filter band of band frequency band, this band, this band, this band. So, sometime n is called frequency band also. Okay. So, now I give you a real problem. That problem is that if you see in here, I will filter bank analysis I will come later on. Let us come in here. If you see, there is a plot we have already discussed, which is called spectrogram. So, this plot is called spectrogram. This plot is called spectrogram. So, what is spectrogram consist? If you see, this axis is the time, this axis is the frequency, and the intensity of the particular frequency is represented by the intensity represent the amplitude of the particular frequency. Amplitude of the particular frequency is represented by intensity. Suppose I want to write a program for this spectrogram analysis. How do I write it? If you see, so I have to know, so what are the parameter I have to set? Window I will come later on, window option, what kind of window I should set. If you see the settings and then spectral, resolution is 32 band. 32 band means that whole frequency, if it is Fs, is divided into 32 band. Okay. So, Fs is divided into 32 band. So, that means that if I want to make it, this is my y axis which is frequency, this is my x axis which is time. I take a small segment of the speech, I take this time. So, this time, this is the time I have taken. Now, if I say this frequency Fs is divided in 32 band, that means this axis I can divide it whole frequency scale in 32 band. Okay. So, n is equal to 32 because it is implemented in FFT. So, 2 to the power something it has to be. So, either it will be 32, next is 64, next is 128. So, that way it will be increased. So, 32 band. So, now for this time this band. So, I taken this signal and analyze DFT. What I will get? I get x, this time instant is 1. So, it is 1 k I will get for this time instant, 1 k I get. Once I get 1 k, if I take the mod, then I get the amplitude spectra. So, this amplitude is decoded into a scale. Which scale? Color scale. What is the color? If it is black, if I say if it is black, then intensity is maximum. So, maximum is 1. If it is intensity is maximum, max intensity is black, and if it is white, then it is intensity is mean intensity is white. So, the value of x1 k will come a value. So, within that value I can assign appropriate color of this band for k equal to 1. This is the first band. Now, for k equal to 2, second band, k equal to 3, third band, k equal to 4, fourth band, I can find out this value and color this block. Again I shifted the time, next block I color this block. So, if I plot that way, I get this spectrogram. If you see 64, if I take it 64, okay, if I zoom it, time domain, if you see there is a band will be visible, sorry. Band will be visible. If you see the line, vertical line and horizontal line. So, this is called spectrogram plot. How do you plot the spectrogram? So, depending on the intensity of the particular frequency component, the color will come, and the band is called band resolution. So, that will come resolution trade-off. So, 2 pi by n or Fs by n is nothing but a resolution of that particular band. So, this is the STFT analysis on DFT view. So, in DFT view I can say, if I want to do that, so I will say take a window, any kind of window effect I will discuss later on. So, if I have a signal, take a small portion of the signal and analyze the frequency using DFT technique, the DFT view of the STFT analysis, we are doing the STFT. Once I do the IDFT, then I can say I can get back this frame again. Okay. Now, what will happen if I just separate this portion? Once I get back, I will have a problem in this junction, because next band is here. So, the signal is continuous. So, but this beginning, this end of the window, I get a problem, because if I say this DFT of x n k is nothing but a frequency response of the signal multiplied by the frequency response of the window. If you see that, it is nothing but a m equal to minus infinity to infinity x n multiplied by the omega n. So, I am multiplying a window function with this thing. So, in frequency domain it will be convolution. So, I can say that frequency response whatever I get, it is a convolution of frequency response of the signal and the frequency response of the window. So, the whatever the frequency response I get, it is a convolution, window effect will be there. So, at the boundary there is a window effect. So, if I do segment by segment and there will be a window effect. So, instead of doing that, what we do? We take a window of let us 20 millisecond and then shifted the window 10 millisecond, that means 50% overlap. So, I analyze for 50% overlap. I will discuss why the 50%, how much amount of overlap we should allow, how much amount of overlap we not allowed, so that we can get the signal back again. So, that we will discuss in synthesis part. So, if I do the 50% overlap, then I get the no problem. Okay. So, that I will discuss why it is 50%, why not it is 60%, 70%, how much is allowable, how much is allowable not, that we will discuss during the STFT synthesis, that is the OLA method and FBS method. So, STFT analysis, what I will do, if I recorded for 4800 sample, so what I will do, I take a window of 20 millisecond, that means 320 sample, then I analyze the DFT, okay, and then I shifted the signal, shifted the window for the next frame by 10 millisecond, means 160 sample, then I get the next frame, do the DFT, then I shifted the again 10 millisecond, I analyze the window and do the DFT, then I get the signal. Similarly, for doing the spectrogram also, what I can do, I can take a signal for 20 millisecond and analyze for 20 millisecond and shifted the time shifting of the 10 millisecond or 5 millisecond. So, this will be 5 millisecond. If it is 10 millisecond, this will be 10 millisecond. If it is shifted by only single sample, then single sample delay. So, if I single sample, then see the computational complexity, 48,000 sample, for 48,000 sample, I have to analyze 48,000 times. So, I will later on I will say what should be the trade off, what is the redundancy is there, that we will discuss then for synthesis purpose also. Okay. So, now depending on the shifting you get the resolution I will discuss. So, next class we will think about what is the filtering view of STFT, then we go for the time frequency trade off and then we go for the synthesis part. We draw the analysis diagram and then go for the synthesis. Okay. Thank you.